Welcome back to the bench. Today I have an update for you about the weather station project. And if you've seen the previous video, you'll probably notice that neither of these boards are actually the same as the ones that were on the previous one. And that's because I've upgraded to use this RFM69 radio, which is not 5 volt tolerant. And both the previous boards that I had were 5 volt Arduinos. On this side, this is the sending side. This is an Arduino Pro Mini, which is very similar to what I had before, except this is just the 3.3 volt version, which means it's running at 8 megahertz instead of 16 megahertz. That should actually just help me in terms of power consumption, although most of the time it will actually be sleeping anyway. So this is just connected up to the radio over SPI and to the sensor over I2C. On the other side here, I have a WeMOS D1 Mini. This is an Esp8266 Breakout, which includes everything necessary to program it. So a regulator from 5 volts and a USB to serial chip. This uses the CH340G, which can be tricky to get drivers for, but once you have them, it works great. And then you will notice that I am missing the SD card, and that's because I didn't want to fool around with getting that running just yet. I sort of ran out of time. But I'm pretty sure that I'll be able to add it on, despite the fact that I'm already using the SPI bus, just by using a separate chip select pin for the SD card as opposed to this, which is how I understand that's supposed to work. But I've never done that before, so I guess we'll find out. I've been really impressed by these radios, the RFM69. And these are the high power ones. So this is the RFM69HW, and there are 4 variants, but this is the HW variant, which just means it has higher power than the RFM69W variant, and those two are separate from the ones with a C in the name, or the RFM69CW and the RFM69 was it HCW, I think. And those just have a slightly narrower board, and I believe they have the same pinout as some previous radio that company used to produce. This is the one that I found that was cheapest, and it's been working really well. So I've been very impressed with these radios, and I'd really like to do an overview video of them at some point, and a range test as well, because as you'll note, I'm not actually putting an antenna on here. That pin right there is an antenna pin, this second from the bottom, and over relatively short distances of 15 to 20 meters, which the previous radios were barely managing, maybe 80% success rate over. Even with no antenna, this seems to be working just fine. And it's also a packet-based radio, so it has a whole lot more network integrity just built into it. So, yeah, once I get over the hurdle of the library, which is a little bit more complicated than virtual wire, this was really quite easy to work with. The fact that I'm able to just switch boards like this is really by virtue of working within the Arduino ecosystem. On this side, I just changed voltage, so that would have worked with the same code anyway. But on this side, I completely changed boards. I went from an Arduino Pro Mega to the Esp8266, which is based off a completely different architecture, has a different compiler, and all of that. But because of the work done in making the Arduino libraries, at least the ones that are based off of standard I/O like SPI and I2C, this just pretty much worked. There were a couple of differences that I'll go into when I'm looking at the code, but overall I've been really impressed with just how easy it is to switch back and forth from one board to another. On the receiving side, I have connected up the LCD, and you'll see that the data is going across. And that little dot is going to be blinking to show you that it updates. I haven't actually figured out the issues I was having with this OLED display. Just sometimes the line that was on this side goes away. I assume that's just because it's whatever is the contents of memory when it boots up, and it just happened to boot up all zeros this time. But this display is larger, which is just much nicer for something with this amount of dense information. But yeah, the information's getting across, and even over distances of 20, 30 meters, it's having no issues, even without an antenna. I have experimented with just putting one of these jumper wires in the, just kind of placing it in the hole where the antenna goes, and that does definitely increase the reliability and the signal strength a bit. But I need to create a proper dipole. And then I'd really like to do a range test and experiment with maybe putting the sensor out a little further away just for fun, maybe in a park nearby, and see if I can get, something like a few hundred meters of range out of it. I've read that you're supposed to be able to do that with these, but we'll see what it's like in my use case. Taking a look at the Arduino code, here we have the transmitter code on the left here, and the receiver code on the right. I went over this code in some detail in the previous video, so I'm really just going to do an overview and a highlight of the things that changed. So as before, we pull in the libraries at the top, initialize the sensor and the radio, set up a packet which will hold the data that we want to send. In the setup, we do all the initialization for our sensors and radio, and then in the loop we basically just fill the packet with data and send it out, and then wait 5 seconds. So that hasn't changed, but what has changed is that this radio is a completely different radio now, and the struct has also changed a little bit. So the radio is the RFM69, and I'm not using the version of the library that comes from Low Power Lab, who's the original author. I'm using the version that comes from Adafruit because their version runs on the Esp8266 as well as Arduino's. But it's just a fork of the Low Power Lab library. The constants here at the top come straight out of the example from Adafruit, which I'll link in the description. The network ID allows us to set up a network which is only consists of our nodes. So basically this number has to be the same on both the receiver and the transmitter side. The node ID is a bit like an IP address or something. It defines this particular node on our network, so this should be unique. In this case, the transmitter has node ID 2, and the receiver has node ID 1. And on the transmitter side, I've put that in a variable so that when I transmit, I can use that variable. I have to set the frequency because despite the fact that this board can only operate at one frequency, the chip on all the different boards is the same. So you have to tell the library which one it is. And then the encryption key, I don't particularly care about encryption in this example since it's weather data, and honestly that could be public and I wouldn't care. But this example had it, so I've set it up just with the encryption key that came with the example. This does actually have to be exactly, I think it's 16 characters. So this happens to be that length. Then we set up the radio, and the numbers here are pins. So pin 10 is the chip select that is being used for this particular device. In my case, on the Arduino Pro Mini, this is pin 10. And these two numbers here are the interrupt. This is the pin corresponding to the interrupt, and this is the interrupt number. So on the Arduino Pro Mini, pin 2 has interrupt number 0. And the true that you see here comes from the fact that this is a high power radio, or the RFM69HW instead of the RFM69W. And that just tells the library that it's capable of using high power. So there are several key differences about this struct that I wanted to go over. The first and obvious one is that we're missing the altitude field. That's just because we weren't using it, and it doesn't really make sense in this particular scenario. I've replaced that with this ID field, which is just a packet identifier that will be incremented every time. It's a 16-bit unsigned value, which means it won't roll over until 65,000 packets have passed. So if we're not close to that and it jumps to 0, we know that the device restarted. And if we miss a number, like it was packet 3 and then it's 5, then we know we missed a packet. So that could be useful for some kind of reporting on how many errors we have had. I'm not using that right now, but we could in the future. The next difference is that this went from double to float. And the reason for that is that on the Arduino platform, a double and a float are actually the same size of value. Both of them are 4 bytes. A double is supposed to be twice the number of bytes of a float, but I guess the Arduino just can't handle that with its floating point unit. However, the Esp8266 can, and so when you declare a double on the Esp8266, it ends up being 8 bytes. So that throws things off for a structure, which really has to be the exact same on both sides, because we're sending the bytes from one directly to the other, and this is how we interface with those bytes. And then finally, there's this attribute Pact, which I'm setting because of padding that would get inserted into this structure before. I mentioned in the previous video that I didn't need it. I think that's because all of the variables were the same type, but now because it's a different type here, I guess it doesn't line up correctly on the memory. So the compiler would align it in such a way that it was very fast to access, but what we want instead is for it to be without any spaces in between the fields, because that's how we want to send it over the network. So this attribute Pact just tells the compiler to get rid of any extra space it might have added. Then we initialize the radio. In setup here, we set frequency, node ID, and network, and these are all set above. I went over them. This radio.setHighPower is possible because we do have the high power version of the radio, and that just enables the gain, the extra gain that is available on this module. And I'm setting the power level of the radio to the highest level, which I will probably dial back for power reasons later once I have everything set up in its final location and I have the antennas set up correctly. But for the time being, I just have it at the highest value. And then I set the encryption key. Down here where we're actually sending, everything above that is the same, except that I have packet num instead of altitude. But here where we're actually sending, it's radio.send with retry, and this receiver is the node ID of the receiver, in this case node 1. And then as before, I give it a pointer to the structure and tell it the size of the packet, in this case 14 bytes. And the if statement is just checking to see if the other side retrieved the packet, which I can actually tell because it's a bidirectional radio link, and so there's an acknowledge that gets sent on the other side. So this OK only gets printed if the packet goes through successfully and the other side is listening. So then let's jump over to the other side. Initializing the radio is very much the same as before. I did comment out the SD card stuff for now because I sort of ran out of time, but I will be enabling that in the future. Here everything is the same as the other example, except that node ID is set to 1 instead of 2. And the pins here on the radio are different. These are set up for the Esp8266. D0 is our chip select pin, D8 is the interrupt pin, and on the Esp8266 the interrupt number corresponds to the interrupt pin, so both they are the same here. The structure has to be identical in both places, and again this float becomes really important because this side is running the Esp8266, and then I initialize the radio exactly the same as on the other side. And then the main difference here is receiving works slightly differently than the virtual wire library. I have this check to see if we have received a new packet, radio.receive done. And if that returns true, then this packet, basically I'm telling the compiler that P should point to the data here, but pretend that it's a packet. All that does is it allows me to read the fields out of this data that I've named in this structure, just as saying which bytes to pull out, and it allows me to use a name for them. So where before it was p.id, here it's p arrow id because p is a pointer instead of being an actual struct. And I should mention radio.data is the data that got sent over, and radio.data len is the length of that data. So I just print all this to serial, and a little bit lower here I check to see if the radio requested an acknowledge, which I suppose is because the send with retry. I haven't looked at the other send functions, but I'm assuming the send with retry, it checks to see if wants an acknowledge. So here we check to see if it needs an acknowledge, and when it does, we send that. And so it's really neat. This will actually know, the sender will actually know if the packet failed, and of course we have the ability to tell the sender that the packet failed if for some reason, like, we can't retrieve the data correctly. If I was doing a CRC check in here, I could simply not send this acknowledge, and that would allow me to signal back to the other side that it had failed. And again, I've commented out the SD card stuff. So other than that, this example is the same, and you've already seen the results. I wanted to go over another pitfall that I encountered trying to get to work with the RFM69 library on the Esp8266. Getting the pins right was a little difficult, but it was actually much easier than I thought it was because of this line right here. Well, not serial. This is done for boards like the Leonardo that have to wait until a USB connection is established before the serial actually is possible to use. But on the Esp8266, this causes a real problem because it goes into a loop. I don't know if it would actually finish, but it definitely doesn't finish before the watchdog timer hits. And so what happens is it causes an error in the console that looks like, a pretty catastrophic code error. And because it happens right at the very beginning of setup, you don't know what's going on, and it's very hard to debug. So I spent a lot longer trying to fix this, thinking that I had the pins set up incorrectly here at the top here. But in reality, all it was that when it hit this line, it was waiting, and then it hit the watchdog reset. And I should have known, because it does actually say watchdog timer, that it was a timing issue. Something was going into a long loop. But for some reason, I was just thinking that meant that the board had frozen up, and then it was getting into a watchdog timer. But anyway, if you do run into that situation where it seems like nothing you do will get it running, check for something like this, because a lot of examples that try to be cross-platform will include it. and that can really get you in trouble with the ESP8266. And that's it for this update. I do have future plans, so stay tuned for those. I obviously need to get this off of a breadboard and into some sort of a more final form, and I would like to do quite a lot with low power. So I'll be adding antennas to these radios, doing some range tests, and also removing the LED and all the other different things that people do in order to get longer life out of their Arduino Pro Minis. I had mentioned that I would like to sort of put this a little distance away and see if I can maybe continue communicating with that over something like 300 meters or something like that, which is about the distance from me to a park nearby, which would be just really fun and kind of a challenge. In order to power it, I would use a solar panel and lithium-ion batteries, so that would be an interesting challenge as well, although at first I'm just going to put it on the porch. So thank you very much for watching. If you're interested in this, please subscribe for new updates and check out some of my other videos. Thank you very much. Bye.